So in this video, we will prove the Pythagorean theorem visually in two different ways. Let's say I have a right triangle. Well, let me take a better one. Let's say this is my right triangle. Okay, my drawing is not going to be perfect. Okay, and this is the right angle right here. Now, the two sides, this side and this side, are called legs. Let's say they are A units long, A units and B units long. And the side that faces the right angle is, let's say, C units long. According to the Pythagorean theorem, the following must hold. A square plus B square must equal C squared. Well, this is a result we are all familiar with, but in this video, we are going to prove why this is true. Okay, that's our goal. In any right triangle, the squares on the legs add up to the area of the square on the hypotenuse. This is the hypotenuse. These are the legs. All right, let's move on. So what I have here is I have four right triangles arranged in this manner. Let's see what's going on. This is a copy of the right triangle that I'm talking about. And I have four of them. Okay, I shaded only one. The legs are A units and B units long, and the hypotenuse is C units. I did arrange four copies of this pink triangle in a very specific way, as follows. Now, first, I have to prove that the quadrilateral ABCD is a square, and the quadrilateral PQRS, which is kind of the square, shape in the middle, is also a square before I can proceed. Once again, I have chosen to arrange four copies of the same pink triangle in this manner as shown in the picture. And first I have to prove that the shape ABCD is a square. It clearly has four sides, but doesn't mean it's a square. And the shape PQRS is also a square. Well, clearly this angle and this angle must equal this angle and this angle. And these two angles that are marked with marked red they add up to 90. So this angle must be 90. And each side is C units long because they are the hypotenuse. So ABCD is a square. In a similar manner, we can prove that the shape PQRS is also a square. If this is 90, this has to be 90. Exact same argument, all four angles. So this shape, PQRS, let's shade it so that we can focus on it. I'm talking about this shape, quadrilateral PQRS. I'm going to shade it yellow. This yellow shape is a square because each angle is 90 degrees and each side is this longer leg B minus the shorter leg A, which is B minus A. So all four sides are the same. All four angles are the same. So this shape, PQRS, has to be a square. Almost done. Now, I can establish that the sum of the areas of these four right triangles and this little square must equal the sum of the area of the square ABCD. Once again, I know that based on my picture, area of the big square ABCD must equal the sum of the areas of the four right triangles and the little square. So let's do that. What's the area of the big square? It's simply C squared. Now, this must equal the area of the little square, which has to be B minus A squared, because each side of the little square, PQRS, is B minus A. And this time, I need to find the area of each right triangle, which has to be A times B, half times height times base, A times B divided by 2, but I'm going to multiply it by 4. I'm going to put my 4 here. Not that it makes any difference. Instead of 4AB over 2, I can easily write 2AB. I can easily write 2AB. And B minus A squared, if you foil it, if you foil B minus A squared, you will get B squared minus 2AB plus A squared. Things are already looking pretty good. Guess what? I can cancel this and this. Okay? And what am I left with? I am left with the result or the claim of the Pythagorean theorem. A squared plus B squared is equal to C squared. So I'm going to do another proof, which will be very similar to this, but I'm going to arrange the right triangles in a slightly different way. So again, as before, I took 4 right triangles, and I'm going to shade one of them, maybe DRS. Pink. This pink triangle, I took 4 copies of the pink triangle and arranged them as I did. This is the next one, this is the third one, this is the fourth one. Now, like before, I have to prove that quadrilateral ABCD is a square. Well, each side of ABCD is B plus A. Okay, that helps. That's my first step. And each angle is a right angle because we're talking about right triangles. So I established that quadrilateral ABCD is a square. What about the quadrilateral PQRS? Well, that's a square too, because each side of PQRS is C and each angle is right angle. This has to be right because this angle these two green angles add up to 90. So the red angle has to be 90. And in a similar manner, you can prove that each angle of quadrilateral PQRS is 90 degrees. So PQRS is a square, ABCD is a square, and what we're going to do is very similar to what we did in our last proof. We are going to claim that the area of the big square, well, it's not a claim, it's obvious. Area of the big square must equal to the area of the little square plus the sum of the areas of the four triangles. So what's the area of the big square? Area of the big square, ABCD, is A plus B and what's the area of the little square? C squared. And what's the area of each right triangle? It's going to be AB over 2, but I'm going to multiply it by 4. As before, as before, I can cancel 4 by 2 and get 2AB. And on the left-hand side, I can multiply A plus B by A plus B, and I will get A squared plus 2AB plus B squared. Now, things are looking pretty good because I can cancel 2AB and 2AB and arrive at our desired conclusion. Done. I just proved using this picture. A square plus B square is equal to C squared.